Hello students, welcome to Educate. We are going to study the numericals of chapter Wave Optics. So let's start. Monochromatic light of wavelength 589 nanometer is incident from air on water surface. What are the wavelength, frequency and speed of refracted light? Refractive index of water is given. So question number 1. C is 3 into 10 to the power 8 meter per second. When light enters from one medium to another whose refractive index is mu, in that case, speed becomes c upon mu. C is 3 into 10 to the power 8 divided by mu is given as 4 by 3. 4 by 3 means 1.33. So 9 by 4, that will become 2.25 multiplied by 10 to the power 8 meter per second. Correct? So we have got the speed and wavelength lambda dash will be equal to lambda divided by mu. So lambda is 589 and mu is either 4 by 3 you can write, or its value you can put and then evaluate. So this will come out to be 0.59, sorry, 444 into 10 to the power 9. Sorry, this is already in nanometer, so just write it nanometer, right? Either here you write 10 power minus 9 and then evaluate, then this will also become 10 power minus 9, right? Then what is left? Frequency C equal to nu lambda. Keep in mind, whether there is reflection, the value of frequency will remain intact. So here nu will become c upon lambda. C is 3 into 10 to the power 8 divided by lambda. Lambda is given in our question as 589 into 10 to the power minus 9. So we can simplify it. So what will it become? It will become 5.09 into 10 to the power 15. 5.09 into 10 to the power 15 hertz. So did we get all the values? Wavelength, yes. Frequency will remain same. Speed we have found, yes. So in case of reflected light, no change will occur. Everything means every factor will remain same. But in case of refracted light, two things will change, and that will be lambda and V. Correct? You have understood. Here question needs two things. What is happening in case of reflected light? So in case of reflected light, you don't have to make any change. Every concept means, be it speed of light, be it frequency, be it wavelength, they all will be same. But in case of refracted light, what happens? The wavelength will change. It will become lambda dash equal to lambda upon mu. Speed will change. It will become c upon mu. And as far as frequency is concerned, it will not change. Correct? Now, we are going to see second question. Second question says, what is the shape of the wavefront in each of the following cases? Light diverging from a point source. So suppose this is point source here. This is point source. Suppose light rays are going like this. So it will be in the R direction. So here this type of wavefronts will be obtained. These are called spherical wavefronts. So in first case, if light is diverging, in that case spherical wavefront will be obtained. If you take point source here, so you can draw rays in all directions, and then you can find the locus at any instant, so it will be circle. So that thing we are talking about. Then light emerging out of a convex lens when a point source is placed at its focus. So suppose this is convex lens, this is source, so rays will go like this, right? And then they all will become parallel. If they are parallel, then what type wavefront will be obtained? So here wavefront obtained will be plane wavefront. Here if we extend it further, so another wavefront will be like this. So these are called plane wavefronts. Correct. So this is case of part B. Then portion of the wavefront of light from a distant star is intercepted by Earth. So obviously, if star is very far, the rays will be parallel. If rays will be parallel like this, in that case, we will get this type of wave, plane wavefronts. Right? So this is the case. So this is answer to second question. Now we are going to see third question. The refractive index of glass is 1.5. What is the speed of the light in the glass? So you remember C equal to V times mu, or V equal to C upon mu. Here in our question, C is given as 3 into 10 to the power 8, and the value of mu is given as 1.5. So this will come out to be 2.0 into 10 to the power 8 meter per second. Correct? Now, second part. Is the speed of light in glass independent of color of light? If not, which of the two colors, red and violet, travel slower in glass prism? Here, there is one formula. Refractive index mu is k times k upon lambda square. What does this imply? Here, V equal to C upon mu. Let's write V red. So C upon mu red, right? And V violet, so C upon mu violet. Now we are going to make a comparison. So here we know very well that this lambda for red color is larger than that of violet color. So if lambda is larger, so we can say mu violet will be greater than mu red, because denominator will be larger. In that case, mu will be smaller. Correct. So if mu v is larger than mu r, then what do we get? Then we will get VR will be larger than VV. I think you have understood. So this concept is being used here. Now we are going to see next question. Next question says, in Young's double slit experiment, the slits are separated by 0.28 millimeter and the screen is placed 1.4 millimeter away. The distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. Determine the wavelength of light used. So here what is situation? Situation is like this. This is S1, this is S2, this separation is D. And here this is screen which is at distance D. Right. Now in our question, information is given. Small d is given as 0.28 into 10 to the power minus 3 meter. And screen is placed, means d is given as 1.4 meter. And here distance between central bright fringe and the fourth bright fringe. Central bright fringe means, suppose this is like this. This is central bright. So this one beta, then second beta, then third 3 beta, and then this is 4 beta. This is first bright, second bright, third bright, 4 bright. So this distance is given as 4 beta. So 4 beta is equal to 1.2 centimeter, or 1.2 into 10 to the power minus 2 meter. So beta will be equal to, divided by 4, 0.3 into 10 to the power minus 2 meter. So we have information small d, capital D, beta, and we have formula. Beta is given by lambda times capital D divided by small d, or lambda equal to beta times capital small d divided by capital D. We can put the values of beta as 0.3 into 10 to the power minus 2 into d, this is 0.28 into 10 to the power minus 3, and whole divided by 1.4, and then we can evaluate. So this will give lambda equal to around 6,000 angstrom. You know angstrom, 10 power minus 10 meter. Now there is another question. The next question says, what is next question? Question says, in a young double slit experiment using monochromatic light of wavelength lambda, the intensity of light at a point on the screen where path difference is lambda is k unit. What is the intensity of light at a point where path difference is lambda by 3? Right? So if you remember, we write the equation for intensity. We assume that intensity of the two sources is same. So here we write I equal to I0 plus I0 plus twice of root of I0 times cos phi, right? And then this becomes 2I0 plus 2I0 cos phi, or further 2I0 we take out, then 1 plus cos phi will be left. But here we can apply half angle, 2I0 1 plus 2 cos square phi by 2 minus 1. So 1 will cancel out. We will get 4I0 cos square phi by 2. So this is I. And in our question, it is given that this becomes, when P is equal to, here it says, when path difference is lambda, intensity is k unit. So we can write here, if you remember, lambda corresponds to 2 pi, right? So we can write in place of here path difference lambda. So for lambda we can write 2 pi. So we write here this value 2 pi, right? So when we write 2 pi here, so what do we get? So this will become 4I0 and cos square pi, right? Cos square pi, and cos square pi will become 1. So 4I0 is value of I, right? And this is given as k, which is k. Now when it becomes lambda by 3, lambda by 3 means what? Here if we make it lambda by 3, then this will become 2 pi by 3, So in place of phi, we write 2 pi by 3. So this will become pi by 3. Pi by 3 means 60 degree. So if it is 60 degree, in that case, what do we get? So here we write 60 degree. So cos 60 is 1 by 2 and 1 by 2 whole square is 1 by 4. So we will get just I0. So I0 means it will become just k by 4, correct? So this is our answer. And now we have last question. The last question says, let's read it. A beam of light consisting of two wavelengths 650 nanometer and 520 nanometer is used to obtain interference fringes in Young's double slit experiment. Find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometer, and then what is the least distance from the central maximum where the bright fringes due to both the wavelengths coincide. So let's see this situation. So third bright fringe. So we can write. So let's write it as x3 will be 3 times fringe width, that is lambda 1d divided by d. Right. Now we can put the values. So after putting values, 3 times lambda 1, in question lambda 1 is given as 650. So we can write 650 into 10 to the power minus 9 into d. So here d is not given, so we just write d, and then here question is incomplete. Actually information of question is missing. Here there must be d and there must be small d, otherwise calculation can't be done. So capital D is given as 1.2 meter, 1.2 meter, and small d is also given as 2 millimeter. So in book there is misprint, or not misprint, but that portion is omitted by mistake. So we can write the value of d as 1.2 here. So 1.2 and then divide by separation. Separation is 2 into 10 to the power minus 3. And then evaluation can be done, right? So this will come out to be 1.17 into 10 power minus 3. 1.17 into 10 to the power minus 3 meter. So this is case of first part, right? We can read it again. A beam of light consists of two wavelengths 650 nanometer, 520 nanometer. It is used to obtain interference fringes in Young's double slit experiment. Find the distance of the third bright fringe on the screen. So third bright fringe means 3 times beta. So 3 times lambda 1d divided by d. We put the value 3 into 650 into 10 power minus 9 into 1.2 divided by 2 into 10 power minus 3, and that comes out to be 1.17 into 10 power minus 3 meter. Now, so this is the first case. Now, second case, we have to check what is the least distance between the central maximum where the bright fringes due to both wavelengths coincide. So we have to consider the situation when the bright fringes of the two coincide. For that purpose, we write the condition like suppose x is equal to n1 beta 1 must be equal to n2 beta 2, right? So just write n1 beta 1 is equal to lambda 1 into d divided by small d must be equal to n2 into lambda 2 d divided by small d. So here what will cancel out? dd will cancel out, dd will cancel out. So n1 lambda 1 must be equal to n2 lambda 2, right? Now we can assume that bright fringes will coincide when suppose in place of n2 we can write n1 plus 1, right? Difference of 1. So if we write n1 lambda 1 equal to n1 plus 1 lambda 2, and then we put the values, so what do we get? So let's rewrite it. So we have obtained up to here n1 lambda 1 equal to n1 plus 1 times lambda 2. So n1 times it is 650 is equal to n1 plus 1 times it is 520, right? So we can open the bracket n1 into 650 minus n1 into 520 equal to 520. So n1 equal to 520 divided by 130. So this will give 5. No, sorry, this will give 4 because this is 520. So this is 30. So this will give 4. So we have got n1 equal to 4. So now we can evaluate x from anyone. So x was n1 lambda 1 d divided by small d. So n1 we have got as 4, lambda 1 is 650 into 10 to the power minus 9 into d is 1.2 divided by small d is 2 into 10 to the power minus 3. Now we can evaluate it to get x, that will be 1.56 into 10 power minus 3. 1.56 into 10 to the power minus 3 meter. So this is our answer. I think you have understood. Thank you for watching. Team Educate.